When we are using elementary operations, we are all the time copying x1, x2, etc. However, only the coefficients in front of these variables and the right hand side are changing. In this video, we will use this property to introduce a shorthand notation for linear systems, the so-called augmented matrix. We will see that the counterpart of elementary operations with linear equations, that those will translate into operations with the rows of an augmented matrix. And this means that we will be able to use the augmented matrix to solve all our linear systems. Let's see, what did we have? We have a linear system over here. We added once the first equations to the second one, got the new linear system, and we can make it even nicer by adding the second equation twice to the first one to get another linear system which is already x1 equals 3, x2 equals 2. So that was our small linear system. And if you have such a small linear system, it's not such a big deal that you're copying all the time the x1s and the x2s. However, you can imagine that as soon as you have 5 equations and 10 variables, that it becomes really a nuisance. So let us introduce a shorthand notation. What do? We introduce a so-called augmented matrix over here. Every row of the augmented matrix corresponds to an equation over here. The coefficients 1 and minus 2 are the coefficients in front of the x1 and the x2. Then the bar, and behind the bar is just the right hand side, minus 1. Well, we have 2 equations over here, so we get 2 rows in our augmented matrix. And how can we start to do the computations? Well, the operations with the rows are the same as the operations with the equations over here. So instead of manipulating the equations over here, I can manipulate the rows over here. So here I added the first equation to the second. That translates into adding the first row to the second row over here, denoted with a plus 1. So we leave the first row unchanged, and we add the first row once to the second row. So I do 1 minus 1 equals 0, minus 2 plus 3 equals 1, and minus 1 plus 3 equals 2. And I get a new second row. And this new augmented matrix corresponds to this second system, as you can verify easily. And then we can go on with the augmented matrix. We add twice the second row to the first row. 2 times 0 equals 0 plus 1 equals 1. 2 times 1 equals 2 plus 2 equals 0. 2 times 2 equals 4 plus minus 1 equals 3. And we get this augmented matrix over here corresponding to this system over here. And then we can translate back. We have 1 times x1 plus 0 times x02 equals 3 over here. So x1 equals 3. And 0 times x1 plus 1 times x2 equals 2 over here. So we get x2 equals 2. Oh, that's fun. Let's do another example. There we are, a bit bigger. Numbers chosen completely at random, as you can see. 1 through 3, 4, 5, 6, 7, 8, 9. How do we determine the solution of this system? As you see, we have 3 equations and 2 unknowns. Is it possible to find a solution? Well, let us try. First, I want to get a 0 over here and over here. So, how can I get a 0 over here? Take the first equation and add it minus 4 times to the second equation. So we get minus 4 plus 4 equals 0, minus 8 plus 5 equals minus 3, minus 12 plus 6 equals minus 6. And we leave the first and the third row unchanged, untouched. Be careful when copying. So easy to make a mistake there. Then we want a 0 over here. Okay, that's not so difficult. Add minus 7 times the first row to the last row. And we find a 0 here. minus 14 plus 8 equals minus 6. Minus 21 plus 9 equals minus 12. And here we have our next augmented matrix. Now it's time to clean up some mess. We see here factors of 3, here factors of 6. So it's convenient to multiply here with minus 1/3, multiply here with minus 1/6. So the numbers become a bit smaller and we don't have fractions. And as you see, both rows become the same. Well, that can happen. So we go on. If we add the second row minus 1 times to the last row, we get 0, 0, 0 over here. No problem. A row consisting entirely of zeros means 0 times x1 plus 0 times x2 equals 0. That's always true, so that's fine. And then we go on a bit. We want to have a 0 over here too. We can take care of that by adding the second row minus 2 times to the first row. We get minus 2 times 0 equals 0, plus 1 equals 1, minus 2 times 1 equals minus 2, plus 2 equals 0, and minus 2 times 2 equals minus 4, plus 3 equals minus 1. And there we are. Then we translate back. 1 times x1 plus 0 times x2 equals minus 1. x1 equals minus 1. 0 times x1 plus 1 times x2 equals 2. x2 equals 2. And 0 times x1 plus 0 times x2 equals 0. 0 equals 0. That's always true. So that's how we can solve linear systems. First, go to the augmented matrix, use the row operations on the augmented matrix, and when you're done, translate back, and there you have your solution.